Yeah, thanks. Well, thanks everyone for coming here for the talk. My name is Gabor Szabo. I work at Twitter as a data scientist. And I would like to talk a little bit about how we could detect possibly topics, bigger subjects in Twitter streams, in tweets in particular, obviously. So that's what this talk is going to be about. We worked on this project with my intern at that time, with Dan Frank. So that's and then obviously with other engineers on productionizing the project. So just as an outline, very quickly in the beginning, I would like to talk about Twitter in general, like probably you know most things about Twitter to be known, but still I would like to just kind of like talk, just give a very short intro, then basically just talk about the problem what we are trying to solve here, and then the methods, then the data that we use for this project, for this event detection. We will see some metrics about these events, the subjects that we can mine from the tweet streams, and I'm going to show you a couple of plots about that and what are the characteristics of the users that contribute to these streams and how active they are. So we can also get a glimpse of, like, depending on the size of the subject that we will see, what are the types of people that are talking about that. And then also at the end some measurements about the temporal characteristics of these events before I conclude. So just about Twitter, as I promised, very quickly. Obviously, tweets are very short messages. They can be of at maximum length 140 characters. This is because originally they were started as SMS messages, and then SMS can only comprise 160 characters. So we had to cater for the username as well in the beginning. So that's why it's so short. But this is also a good medium for like very quick updates. And then users usually follow other users based on their interests. So the way that we like to think about this social network is that this is an asymmetric follow network where you don't necessarily have to reciprocate the links that people make to you. But in fact, if you are a celebrity or an opinion leader or whatnot, or just like a normal person, then the followers can get updates from you, but you don't necessarily have to follow them back. At this point, we have more than like 280, 290 million users a month. They are sending a lot of tweets a day, so that's why I just put there the statistics, like 500 million tweets, because this is the amount of data that we have to kind of cope with at this point in the algorithm, and so that's the challenge basically, that you have to figure out what some of these 500 million tweets talk about in a day. The majority of our users are on using mobile phones, and as I mentioned several times, Twitter has this very timely nature where tweets are usually like these fleeting messages. People see something, they talk about that, or they hear something in the news or news about something, then they tweet that. So that's why it's also like interesting to find out automatically what kind of events are happening there. And so there are obviously the big events there that happen, that people talk about on Twitter, but there are also smaller ones, and then we would also like to see whether we are able to capture also those the smaller events. And then because of this distribution between the large and small events, we will be able to see that there is like this long-tail behavior in the size of the events. That's perhaps kind of like a reflection of how kind of the importance of news that actually happen in real life, right? So there are like very important news, but only a few of them, and there are like not very important pieces of information, of which there is a lot all the time. So we would like to see what people talk about publicly, basically, and that's what this service is for, and then automatically find these events. Now, when we talk about events, right, we haven't really defined what an event is up until this point, because it's not very obvious what they should be, but we have a feeling that they should be about the same topic. So textually, they should use the same words, the same key expressions. They should refer to the same people, same entities, but obviously for an algorithm, that would be the most that we can achieve, that we match up text with each other in the tweets. So they also pretty localized in time, which is very important, right? So when an event is happening, there is a what component of the event, like what happened and then when it happened, because that's what the important thing is. Otherwise, if it's spread out in time, or when people say good morning to each other every single morning, that's not very interesting. That's also an event, but probably not of a very high interest to us. Another requirement that we wanted to see with this project is that we know that when there is an event happening, then there are also like subjects that relate to this main event, but they are not. But they also can have a life of their own. So if there is like say a big storm somewhere, then there could be news or pieces of news about this big storm, but there could be news about some floods in an area, and then that should be more important to the people that live in that area. So that this is what we mean by the hierarchical structure of events, that it can evolve in time and that it can give rise to like new little sub-events. I'm going to show you examples about like how we approach this. The purpose of all this is obviously like we could show updates to our users about the events. So this is about news discovery, personalization. If you are interested in something, then we could show you events that are about the same subjects. And then for targeting, say if you think about the targeting vehicles that we use, the promoted tweets, then we could figure out what events people are interested in. Say this conference, then we would know who are the people who are interested in text analytics, because we know that this event is happening right now. And then internally, for my team, we were more interested in the analytics part of the outcome of the results here. So basically, there is a lot of tweets, as you could see, coming in all the time, like 500 million a day. And so that's why we should choose models that are very minimal, that are just very fast to execute. And that's what I'm going to show here in a second. And because tweets are very short, very emotional most of the times, and require very little effort on part of the user to write, they can have like the words that express what the user is talking about they don't always make sense. So they are sometimes slang words. The sentences are not full and so on. But there is usually, because they can be only so short, there is usually one or two keywords in there that reflect on the event. And so that's a good thing, that either the hashtags or some keywords there, they in particular refer to that. So that's a good way to correlate these, to find the correlations between the tweets in terms of text. But of course, if you think about how we would normally find documents in a big document set that are related to each other, then you would use like normal document processing techniques. Here, it would be hard pressed to do this because these tweets are so short. So if you think about like using TF-IDF to give weights to terms, that's going to be a bit hard because one document is so short here. They are just like 5 words at most and so on. So that's why we consider a document as a set of tweets. So basically, we are going to pull tweets together and consider that as kind of a smaller or bigger document that relates to that event. But obviously, it's not going to be a document like a legal document that you would normally see. And then, of course, there's a lot of noise here. So there's a lot of spam in the system. There's a lot of kind of non-events that I just mentioned, like people saying good mornings to each other. So that's not very important. And so that's why we prepared the data. We looked at the tweets that are coming in, tried the clustering a few times, and basically we boiled it down that we need to obviously do the proper stemming of the words. In this case, we use the snowball stemmer, and then we have to remove the punctuation and the @mentions and hashtags, and that's when you are left with the keywords in the tweets. So that's the normal way to prepare text. And then, obviously, there are different languages on Twitter, but in this case, the examples I'm going to show you just relate to English, so that's only English language tweets. And then, so basically, this requirement of having a very simple algorithm was kind of we chose to implement it with a streaming clustering algorithm. In which case we only had to have a limited memory in terms of storing all the tweets, because obviously you cannot store like a billion tweets all the time and then try to do some clustering on them. So we had to have a streaming algorithm that only has a finite amount of memory assigned to it, and then obviously the parallelism was a very important factor so that we can distribute the workload. And then, of course, we didn't want to have very strong human supervision in this, so we didn't want to hand label the events that come out. And of course, speed is important, and then we can also check how topical the clusters are that we are finding here. and that we can do with the hashtags. So we kind of kept back the hashtags to be labels for the tweets, to be labels for the events. And then that way you can find how pure the clusters are for the events in terms of the hashtag usage. The algorithm that is this clustering of the tweets, again, like imagine that we have this streaming, all the streaming tweets, and they go to like different worker machines in parallel. So in this case, the clustering works in such a way that again, when the tweets are coming in, you would like to see whether there is already something in my among my clusters that are already similar to these tweets. If there is already a cluster that's kind of growing in topics, then I assign that tweet to that cluster. So that's what I mean by this leader-follower type of clustering, which is, by the way, it's a usual way of clustering items in a streaming way. So we start with a clean slate. The new items are coming in. If they are not similar to anything else yet, based on our cosine distance, then we just start new clusters with them, and then they will be the seed for that cluster. But as more and more tweets are coming in, they will be assigned to the closest cluster. And if the closest cluster is even further than a specific distance, based on this cosine distance, then we start a new cluster. So as I said in the beginning, and so this is a way to basically pre-cluster these tweets. In a way that we will now, that each basically this worker machine will see just, say if we have 10 workers, 1/10 of the stream, and then it will do this leader-follower type of clustering, where we would have at the end of this run, or like continuous during this run, kind of like clusters that are growing, but they are similar to each other textually, right? So the tweets are mapped to a bag of words, and basically we are just looking at the cosine distances between the clusters and between the tweets and the cluster centroids. And then so this gives you something, but you can already see that by kind of randomly distributing this workload among like these 10 worker machines, we will have the same clusters like forming on all the parallel distributed workers, because if you just like randomly shuffle around the tweets, then the same topic may go to like different machines, of course. So this is not going to be good if you want to, so at this point you will have the same topics distributed across different machines that do not know about each other at all, if we didn't do any kind of like a secondary stage of clustering or processing. So that's why what we did as a second stage, so this is the first stage, which is really fast. So with this you can eliminate spam by various ways, and you can cluster these tweets basically that into the smaller or larger first level clusters. They could have like between 100 to 200 tweets. So I will in the next slide I will have the second stage of the algorithm that's easier to understand. But the data that we used here, basically, as I said, the English language tweets from US users. The users also had a high reputation score that we use kind of internally. This is like how reliable that user is. So if there are good followers of the user, then they also be good. Basically, they will have a high reputation. If people with high reputation scores follow each other, then again, like there will be a reinforcement between their reputation scores. So this is this authorities hub model that we kind of use inside. For these examples, I just took a sample. It was like 5%, and at the beginning of this project, this is data from 2012, so about 2 years ago. This is just for the analytics for that, and later on we worked on the implementation of this. The timestamps are obviously important for the tweets because that gives you the time locality, the temporal locality. So you also, when you are creating these clusters in this parallel fashion, at some point you also want to say that, hey, now I'm going to stop because this cluster hasn't seen any more addition in a little while, right? So when I'm growing these clusters, and then I'm stopping it, I think this cluster is done. This document is done now about this subject. And so that's why it's important. In this case, we have a sample of 100 million tweets here with tens of millions or so of authors. And at that time, when this data was taken, there were a couple of interesting events going on worldwide, or at least in the US, since this is US data. There were the presidential elections happening at that time. The unfortunate event of this Hurricane Sandy also hit at that time, and then there was Halloween happening. And for the further analysis, we can also use the past, so just in terms of data, we can use the user's past activities when I can show like how active users are. So we also use that data just to be complete. So this is the second stage of the clustering that I was referring to. So the first stage with this leader-follower type of clustering, then we take care of like quickly just having a coarse view of the events that happen there. But now we have to merge this information together so that we know that when the workers are seeing this, the same topics, then basically they will be brought together into one here at this stage. So this stage is different. This stage is just run on one kind of strong computer that has like enough memory and processing power. And then basically all these the clusters together with the centroids, they are pushed onto this one machine, one server here that will perform this bottom-up clustering. So we are probably familiar with this. If we have items that now again represent documents based on the weighted sum of the tweets using the bag of words for the tweets, right? So each tweet is a vector of words. Then we are just summing up the vectors, and that's going to be the centroid of that little cluster there. Now we have these items that we want to cluster further here in this agglomerative clustering. So here the two most similar clusters are first brought together into one, and they will start forming one new cluster. Then we decrease by this, we decrease the total number of cluster items by 1, right? So it's n-1. And now we can do the same thing again. We can check which two clusters are now more similar to each other. And then we bring those also together. So that gives you basically, this is the operational view of this clustering. And then that's why it's agglomerative, because it agglomerates clusters together. But it also gives you a nice view of the hierarchy of the events that happen, right? Because here, if you imagine that on the leaves, of this dendrogram. So this dendrogram kind of symbolizes these merges that I was just describing, these agglomerations. So on each level, each like horizontal line is a distance at which two clusters were joined together. And then you can see somewhere here that, for instance, the big cluster, or like actually a small cluster, but a bigger one here. So they were joined at a distance of about, I don't know, 0.5 in terms of like cosine distance in the end. And that means that they are not that similar to each other, so they were like pretty far from each other, but they were still closer than, say, something on the left-hand side of the dendrogram. So this way, you can see that if you now look at the leaves of this dendrogram, these will be events that people talk about, and then these merges, the height of these merges, will be how similar those subtopics are to each other. So that's the way that we are looking at basically subtopics and their hierarchy, because this way, just from the textual similarity, you can see that how far is one event from another. And by the different colors, I just colored like sub-branches of this dendrogram. I just made a cut at 0.7 distance, and then anything below that sub-branch was colored the same way, so that you can see also visually what is the topic that was formed by the tweets within the sub-branch. And then the way that I kind of refer to that we have to remove spam, that's an interesting trick that if you basically look at these clusters, so initially we don't try to remove spam in any way, but if you look at clusters that form in this first leader-follower type of clustering, then many times you will see that they are all they use the same words. They all kind of like want to take a survey so that you can get an iPhone, right? And they all use the same words there. So the word entropy within these clusters will be very low, because it's all the same words. But if this is about a nice real event, then the word entropy will be pretty high, because people always use like different words. So that's the way of basically like filtering out for us the spammy tweets, or the spammy clusters. When it's all about the same thing, then it's not interesting. And those are all to the left-hand side of this process. There's a lot of like these clusters that I'm not even showing here, and those are the spammy ones. And then, so just to show you examples, these were the events that happened at that time. So I just plotted basically these word clouds for the sub-branches. So imagine that each sub-branch, right, so the yellow one here, for instance, on the right-hand side, this is about something. there are lots of tweets on the right-hand side within the first level clusters, and then they all have the stems of the words. So you can see that if you do this, that indeed you will discover that this big yellow cluster is talking about the elections at that time, right? So there are debates there, Biden, Romney, Obama. You can all see the suspect words in there. Another interesting one, for instance, here, this little purple cluster. Again, it's barely visible there, but it's there. So this way, you can see that people are talking about the same thing. It's about pumpkin carvings, all right? So this is about like Halloween, October, November at that time. And then again, you can see that without us doing like anything, this comes out from just automatically from this clustering. Maybe, like less kind of popular topics or subjects. These PSAT tests were administered at that time, so the students were talking about that. You can see some sentiment around that I'm afraid of that, or I don't know what I'm gonna do, and things like that. There is this Kendrick Lamar, this singer, artist that released some album. Again, you can see all that happened then. And another use case for that is that you can also see like how people feel about that, right? So the sentiment, you can see there that I like this, I love this, I don't, and so on. And then so just looking at one event there, you can also see that how it was perceived, basically. There is another big event here was Hurricane Sandy, and again you see that here, probably this one next to the election shows a very strong kind of substructure. You can see that there were like sub-events here. It all refer to the same event, but basically because it went on for a longer time, that's why you can see that there were like several developments around that you can capture with this clustering as well. And then, so this was for instance the example for the clustering, for this hierarchical clustering. And then now we can look at just in the next couple of slides about like some statistics about these events, like how big they are, what kind of users contribute to these events. So in terms of the sizes, the first thing that you can obviously look at is like how big these events are going to be. So here I basically performed this clustering, and then they looked at how big these clusters were once I did that. And then obviously you can plot the distribution of the size of the clusters. And that's the exact same plot, except that on the left-hand side, there's this double logarithmic rescaling, where you see that this is a very, very straight line there. So this means, this is the same on the right-hand side. So this means that basically if you take the size of the clusters, in other words, the kind of the size of the topics, or maybe the interest in the topics, you can see that it shows like a very, very kind of like a regular, this power law behavior that you see in a lot of other social media settings in terms of user activity. Is everything. And that means that basically there are, maybe in this case, it's much easier to see that clusters that only have two tweets, you have quite a few of them. In this case, let's say like 50% the bottom two tweets. But as you go the cluster size, you will have very fast drop-off in terms of the number of clusters. And that means that of the large clusters, of the very important events, there are only very few, right? That means that, yeah, the very popular events, there are just so many of those. But this is again like the same as everything that you see. So the same for the word usage distribution, the zips laws and all that. So they all show the same power law behavior. And we could ask ourselves that why is it so? Why is it so that there is like we show this very strong regularity? I mean, I was very surprised when we saw this like very straight power law across many decades there in terms of number of tweets, and how could we model it some ways? Could we give a reasonable model of how topics are formed, at least on Twitter, and then maybe real times as well, like in real world as well. And so for that, we came up with something, and this is more like kind of just a thought experiment, but I wanted to share it with you because maybe you are interested in like how we could look at things like that analytically. So imagine that for instance, I will come back to why this analogy may hold, but imagine that we have urns that can contain balls, and we are going to drop balls in these urns. But we don't have a fixed number of urns. They can be, we can add urns to our system, basically. So in every time step, or we continuously introduce these new balls, and we are going to drop them in urns. But the interesting part here is that we just, with a given probability P, here let's call it P, we also can create a new urn. So when we have a new ball, we can either drop it into one of the existing urns, or we can create a new urn and drop the ball there, right? And so with this probability, we create a new urn. But if this probability doesn't hold, like in most of the cases with 1 minus P, then we just drop it into one of the existing urns. But that we choose which one we choose, which urn do we choose. We will choose it with a probability proportional to the number of balls that are already in that urn. So basically, if an urn already has a lot of balls in it, then we are going to drop it. We are going to drop the ball into that urn with a much higher probability. But this is going to be proportional, linear proportional to the number of balls. So why is this relevant? I mean, why did we do this detour? So basically, if you think about urns as topics and balls as tweets, so a new piece of contribution to that topic, then if you were to run this model, then you would get back the exact same kind of power law distribution as you saw in the previous slide here. So the number of balls in the urns is going to follow something like this. And the slope, so how fast it decays, that depends on basically the parameter P that you choose for this introduction of new urns. So you could say that, yeah, I mean, we could maybe give a very simplistic view of how people contribute and create new topics or new news. And this is this way that basically there is like an infinite number of topics out there that people may contribute to, may write about, and then they can choose to contribute to one. And then if they have seen that there is a very important topic out there, very important subject, or just by themselves, somehow there is this intrinsic importance of a topic, they contribute to that, then they, you know, in this picture, they drop their ball into that topic, into that urn. However, there could be like new topics coming up all the time. So in this case, they just tweet about something completely new. And so this gives you this dynamic creation and contribution, which sort of may explain how people are talking about topics. And this also is similar to this very kind of famous realization of rich will get richer, where the people that already have a lot of connections, for instance, in social networks, or even like in financial terms, of course, the people, for instance, with a lot of connections, they get more connections because others already see that they have a lot. That's why they're going to connect to them. So it always works like that. And but this model perhaps is closer to a picture where people choose topics that they can write about. So the other thing that we can basically look at is how users are different between these topics. So we can also ask that, yeah, we have now, say, one topic that people can talk about, but what is the profile of the users that are going to write about that topic? And in this case, what we did was basically we just took the topics, and then we characterized the topics with their size, right? So the size would be the importance of that topic, and that's on the horizontal axis, and the vertical axis. For each size of or for each cluster, we looked at the previous number of tweets sent by the people that talked about that topic, right? So this would mean that if that there is user, say there is Joe who writes about something, who tweets about something, we know in which cluster, in which topic they wrote that tweet about, and then we also know how many times they tweeted. So if we average over the number of tweets that people previously sent for a given topic, then that would give you kind of the overall activity of people that contributed to that topic. And so what you can observe here is that if we average over, if we take like grand averages for all the topics, and then classify them by their sizes, then you can see this kind of this slight but significant decrease, especially here in the beginning of the plot, where you can see that if we go higher and higher with the number of tweets in the topics, then you will get less and less active people there contributing to that topic. So the question why we asked this was that, is it possible for us to basically bring people back or kind of like motivate people to tweet about subjects that are more or less popular overall in the general sense? And it seems to be so that even without kind of any active intervention, we can see that topics that are more popular overall, so which are towards the right-hand side of the scale, they will get less active people also talking about them. And so this was kind of for us interesting because, or just in general, it may be interesting because then it means that if something gets really big, if a topic gets like really popular or widespread, then maybe also the less active users, in other words, those users that usually just tweet less, they will also talk about that. So in other words, this could mean that if I want to create a service that lets people know about like upcoming events or something or like important things, beyond just personalization in terms of like shared interest, you could also try to see whether that event in terms of its volume hits the threshold for that user's kind of own activity profile. You can, in the very same thing, you can also see in the number of retweets, the decline is probably, well, different scale, so I'm not going to say that, but there's also a decline in the number of retweets when we look at the retweets instead of the tweets. So this is exactly the same plot, except for looking at retweets. So less active people contribute to bigger topics. Now, when we look at the kind of the network activity of the users in terms of how many follow links they created, right? We also see that. Now we can see kind of the opposite. So as we go to like more important topics, we will see that the people contributing to a more popular topic, they will create more follows. So that was counterintuitive to us first, and that's why I'm kind of showing this, is that they are less active in terms of tweets, but they're creating more links. So the way that we could kind of explain that to us is that these people are sort of the consumer type, that they are there on Twitter because they want to read tweets. They don't necessarily want to kind of like always write or like tweet, and that's why only when it's very popular then they tweet. But they are also the ones that like to follow a lot of people, so they like to like get information rather than produce information. In terms of the number of followers received, we kind of saw a flat contribution plot. Again, like huge noise, so we don't have to like read a whole lot into that, but it could also mean that people, they don't differ so much in terms of like how important themselves are when they are contributing topics, right? So when I say how important themselves are, I mean that a person that follows a lot of, person that receives a lot of follows, that, you know, that's a lot of follows received, but it doesn't really matter if you receive a lot of follows or not, you will like contribute to the same amount to topics. Just very quickly about the temporal characteristics of these events. So when you look at the length of these events, and then how many number of tweets events get, now we chose to plot it this way, that here on the left-hand side, you can see that how many minutes it takes for the event to come from the beginning when we start seeing the first tweets up until the end when it dies out. Now you can see that it's kind of like it's an increasing curve. On the right-hand side, you can see we kind of rescaled one of the axes, the y-axis, that it's more or less kind of exponential, a very slow exponential, but it's exponential, so it's like increasing. But you also see the interesting thing I would like to point out, two kind of the peaks there, at 1 hour and then at about 2 hours. So this would mean to us that without really like looking into detail about these events, that's this kind of like pre-arranged events, like say this conference, right? So you are sitting in one of the talks, takes about an hour. That's when people are talking about events, or in a movie, TV show, whatnot. While it lasts, people are talking about that. And there is this definite 2 peaks at 1 and 2 hours. So maybe relating to this daily rhythm. And so basically, this was the topic that I wanted to talk about: how to identify topics in big, large amounts of data in a streaming manner, and how we created this hierarchical description of the subjects and the types of the people that contribute to those. And if you have any questions, yeah, please ask me now or even after. Thank you very much for your attention.